Let's investigate the properties of groups, fields, and vector spaces. First, let's begin with groups. I'm going to have to introduce a lot of mathematical notation in order to define a group. So first of all, a group needs to have a set of elements. And I'm going to denote that set by capital G. And it also needs to have an operation. And I'm going to use this dot to denote the operation. So this is a very general concept in abstract algebra. It is a structure that has some axioms that it must satisfy. And I'm going to go through all of those axioms, and I'm going to explain the notation that I'm using for those axioms. But the fundamental concept that we're dealing with is a set with some elements that it has an operation defined. So what are we doing with that operation? We're taking two elements in the set and we're combining them together. And when we combine them together, we want to have another element that is in the set. That property is closure. I'll write that property out over here. So closure is telling us that for any two elements, we need the combination of those elements. When we use that operation, we need that to also be in the set. And I'll write that out formally. I'm going to use this for all symbol. So an upside down A is the for all symbol. So for all elements A and B that are in the group capital G, so this is some set notation over here. This is just saying A and B belong to this set G. This is an element, right? A and B are both elements of G. So for all A and B and G, I'll put a comma over here so it's easier to read. I want A combined with B using the dot operation over here, A dot B. I want that to also be an element of the set G. So if this axiom, we can call it an axiom, we can call it a condition or a property, if this is satisfied, then we have closure. The group is closed under this operation. And this operation could in general be many different types of operations. And we'll get more into what kind of operations we're dealing with later in the video. So this is the first property of a group. Sometimes it's not actually included as a fundamental axiom of a group. It is implied with the definition of this operation. So we need the operation to satisfy closure. Now, one of the axioms that is usually stated first is associativity. So I'm going to write associativity down next. Again, I'm going to use this for all symbol. So for all A's, B's, and C's that are elements of this group, they're inside that set, capital G. I'll put another comma over here so it's easier to read. I want the following associative property to hold. So if I group together A dot B, and then I combine that with C, that's going to be equal to A dot B dot C. So just the groupings over here, where I put the parentheses, which one of these guys I evaluate first, that does not matter. That is the associative property, also known as associativity. If this did not hold, then we would be in trouble. A lot of basic arithmetic relies on the associative property of addition and multiplication. So these guys are operations that satisfy this property. So this is one of those essential axioms of group theory. Now I'm going to introduce two more of these essential axioms. So the next one is the existence of an identity element. So I'm going to write that out formally. What we have is, I'm going to use a notation over here that is slightly difficult to understand when you first see it, because it kind of looks like hieroglyphics, but now when we explain it, it's going to make a lot more sense. So I'm going to use a backwards facing E. So we're going to have there exists. This is a backwards facing E. That is just a condensed notation for there exists. There exists at least one element in the group, and we're going to call that element E. And it belongs to capital G, it belongs to that set, such that, I'm going to use this colon, that means such that. There exists an element in G such that for any element A in the group G, we want the following condition to hold. If I take A and I combine it using the operation with the identity element, I'm going to get back A. And that is the same as combining the identity element with A. So E over here is the identity element. And it makes sense to call it the identity because in general, it's actually going to be unique. There's only going to be one identity element in the group. So that is the condition for the existence of an identity element. Now, another related axiom is the existence of inverses. So we want inverse elements for all elements in the group. So I'll write that down underneath. We're going to use the for all symbol again. For all A in the group G, so for all elements of the group G, I want there to exist some other element, which I'm going to denote by A with a -1 in the superscript. Now that comes from the reciprocal notation. So if you take the -1 power, that is the same as taking the inverse element for multiplication. So this notation I'm going to use, and that's going to be the inverse element. And I want there to exist an inverse element such that if I combine A with its inverse element, I get the identity element. And the ordering does not matter. I can take the inverse element and combine it with the element A. So that is the condition that I want. So these conditions are essential for a group. We need to have a set G defined with some operation, which I'm denoting by dot. This is some general abstract operation. And we need to have closure. We need to have associativity. We need there to exist a unique element that is the identity element. That is what this line is telling us. And we need every element to have an inverse. So that is what these guys are telling us. So now what I'm going to do is I'm going to read this out in plain English. So all 4 of these properties, I'm going to read them out in plain English. For all A's and B's inside the set G, I want A dot B to also be inside the set G. That is what this is telling me. So if I combine any 2 elements, that remains inside the set. And that means the set is closed under that operation. And that's that operation denoted by the dot. Now, the associative property. For all A's, B's, C's inside this group G, if I take A dot B and then dot that with C, that's the same as dotting A after I've already evaluated B dot C. So that is the associative property. Now, this property I'm going to read in plain English. There exists an identity element E inside the group G such that for all elements A inside the group, A dot E is the same as A, which is equivalent to E dot A. So using this operation to combine any element with the identity element gives back the original element. And over here, we have the existence of inverses for all the elements. So I'll read this out in plain English. For all A in the group, there exists A inverse in the group, such that A dot A inverse is the identity element. And that's the same as A inverse dot A. So in general, you don't have to use this notation for the inverse. You can actually put a minus sign out the front. Now that is sometimes more convenient because sometimes you're going to run into groups that are called additive groups and some are multiplicative groups. For additive groups, it makes more sense to put a minus sign because for addition, subtraction is actually addition by the additive inverse. So that is what negative numbers are. So this is one way to think of negative numbers. So subtraction is actually encompassed by addition. It is just adding the additive inverse. And multiplication for a multiplicative group, what are we going to have here? For a multiplicative group, division is the same as multiplying by the multiplicative inverse. And for additive groups, the identity element is usually denoted by 0. And for multiplicative groups, the identity element is denoted by 1. So we're going to use that when we define a field later in this video. So these are the fundamental, essential properties of a group. This guy closure is sometimes just implied in the definition of the operation. But these 3 over here, these are the fundamental axioms. So associativity, the existence of an identity element, and the existence of inverses for all the elements in the group. Now, let's introduce one more property. And that property is called commutativity. I'll write it out in formal notation over here. For all A's and B's that belong to the set capital G, I want the property where A dot B is equal to B dot A. So the order in which we combine these elements does not matter. So A dot B is the same as B dot A. And if that property is satisfied, then we call this a commutative group. If it satisfies commutativity, then it's a commutative group. Another name for this property is actually an abelian group. So I'll write in brackets over here, abelian. So an abelian group is the same as a commutative group. Those are just two different names for the same thing. And Abel, that's the name of a famous mathematician. So an abelian group over here, that is the same as a commutative group. There are also groups that don't satisfy the commutative property, and those are called non-commutative groups. A non-commutative group is the same as a non-abelian group. So those are groups where these axioms hold, these properties are all fine, but this final property does not work. So you can't actually swap the order. Swapping the order is not the same. So in general, you're going to have a non-equal sign over here. But we're going to use the concept of an abelian group to define a field. And then we're going to use the field to define a vector space. So let's move on to fields. So right down over here, we're going to use some similar definitions, and we're going to define a field. So a field, I'm going to denote by capital F. So I'm going to have capital F, and I'm going to use some similar notation to that for a group over there. A field has not just one operation, but it has two operations. It has addition and multiplication. So we have addition and multiplication. And what do I want from these operations? I want to have two separate abelian groups. So I'll write these guys down here. So I want abelian groups. I'm going to write this over here. I want an abelian group for addition and one for multiplication. But it's not as simple as that. So I'll write it down formally. So we have two abelian groups. One of those abelian groups is going to be F with addition. So F is the set, the field, and addition is the operation. And the other one of these abelian groups is going to be the set F excluding the zero element with multiplication. So these guys are both going to be abelian groups. And I have to exclude the zero element over here. And there's a reason for that. If I included this zero element, then it would not be a group, because it would violate this axiom over here. I need, for any A in G, there to exist an inverse element in G, such that if I take the element A times the inverse, I need that to be the identity. And if I include 0, there is no multiplicative inverse. That's the same as saying that you can't divide by 0. Dividing by 0 is going to cause a lot of problems, right? There's no meaningful definition for that. So that's why we have to exclude the 0 element. And this notation over here is just excluding the 0 element from this set. So this is a set that contains all the elements of the field, and we're just excluding that 0. And if we exclude the 0, then every other element has a unique inverse. So we have this quantity is, or this statement is satisfied. So that is the first thing that I want to talk about for fields. And what I want to also stress upon is that the identity element is not the same for these two groups. For this group over here, the identity element is 0, because this is an additive group. For this group, the identity element is 1. So 1 is the identity element here. This is a multiplicative group. The operation is multiplication. So this is 0 and this is 1. The multiplicative identity is 1 and the additive identity is 0. And both of these are abelian groups. So that means in addition to all of these axioms, the commutativity axiom is also satisfied. So that is why we have to specify that these are abelian groups. Another way of saying it is they're commutative groups. So what we also want is a way to link these two operations together. And that property is called distributivity. I'll write down the property for distributivity. So what we want is for all A's, B's, and C's that are elements of the field, now we're talking about this field, we want some properties to hold. We want, if we take A times B plus C, we want that to be the same as A times B plus A times C. Can you see what this property is? I'm just distributing this A with multiplication. So A times the sum of B plus C is equal to A times B by itself plus A times C by itself. Another way of looking at it is if we have a sum and then we multiply by some other element of the field, B plus C times A, that's the same as B times A plus C times A. So here we have B and C, and we've distributed that A. So this distributivity property, the distributive property, that actually links together addition and multiplication. Addition and multiplication are linked together by the property of distributivity. So a field is actually two groups with this distributivity property that links the two operations together. But we have to always remember that when we're thinking about this multiplicative group, we have to exclude the zero element. We have to exclude the additive identity, because the additive identity, 0, does not have a multiplicative inverse. That's why we're excluding it here. All of the guys over here, all of the elements inside that field have an additive inverse. In general, these guys are not equal to each other. So 0 is not equal to 1 for the fields that we're dealing with. So the additive identity and the multiplicative identity are two separate elements in the field. Now we're going to use the concept of a field to define a vector space. I'll do that over here. So now we're going to define a vector space. So we're going to have a vector space. I'll write it over here. We have vector space. And I'm going to call that vector space capital V. So for a vector space, we're going to need a field and a group. So I want a special type of group. I want that abelian group again. So I'm going to need an abelian group. And that abelian group, I'm going to use this bracket notation again. I'm going to have the vector space V with the operation of addition. So I want to be able to add the elements of the vector space. I also want a field. And this field, I'm going to use this notation. I'm going to have F, and this field is going to have addition and multiplication as the two operations. Now, before I continue on with this vector space, I want to tell you that there are alternative ways of defining a field. So over here, I've chosen to define a field in terms of two abelian groups. But what I also could have done is I could have written all the axioms for this group and all the axioms for this group. And then we would just have a long list of axioms, including this distributivity property. And those would be the fundamental axioms or the essential properties of a field. But instead, I've chosen to write it in this condensed form. This, I think, is much more convenient to work with. Because if you understand what a group is, then all you need is to understand two separate abelian groups and this linking property of distributivity. And that is going to tell you what a field is. Alternatively, you can also do another alternative definition. Instead of having addition and multiplication over here, you could choose to have 4 separate operations. So you could have addition and subtraction, multiplication and division. But we know from this property over here, from this inverse property, that subtraction is the same as adding an additive inverse. And division is the same as multiplying by a multiplicative inverse. So in an additive group, we would call these inverses negative numbers. In a multiplicative group, we would call those inverses reciprocals. It's like 1 over a number. Right? So it will take an example. If you have 3, what is the multiplicative inverse of 3? Well, it's 1/3, 1 over 3. It's the reciprocal. But if we're dealing with an additive group, what is the additive inverse of 3? Well, that's -3, or -3. If you take 3 and you add -3, you get 0. 0 is the additive identity. And if you take 3 and you multiply it by 1/3, that's 3/3, that's equal to 1. And 1 is the multiplicative identity. So that's just another way that you could write the field. You could write it in terms of addition and subtraction and multiplication and division. But we know that addition actually encompasses all of subtraction and multiplication encompasses all of division. So that's what we have for a field. And now we're using a field and an abelian group or a commutative group to define a vector space. So V is the vector space and F is the field. So these elements, the elements of the vector space, I'm going to call vectors. So a vector is an element of the vector space. And the elements of this field, I'm going to call scalars. So this can also be called a scalar field. So we have vectors and scalars. In a lot of introductory physics, you're usually taught that vectors have both magnitude and direction, whereas scalars just have magnitude. So now we have a more sophisticated definition. Vectors are not just quantities with both direction and magnitude, but now they are this complicated abstract algebra definition that satisfies a bunch of axioms. So a vector space contains vectors. A vector space is where the vectors live. Now let me write down some of the other properties that are essential over here. So I have an abelian group. That means there is an identity and there are inverses for all of these guys. And I also have the associative property, and this is closed. This field satisfies all the axioms of a field. So now I'll continue writing some other properties over here. If we consider two vectors, I'll call them u and v. They are elements of the vector space. And I'm using this little arrow notation just for familiarity with a lot of physics. And let me consider alpha and beta, these two Greek letters. I'm going to use them to denote scalars. They are elements from the scalar field F. If I scale one of these vectors, if I take alpha times one of these vectors, that is also an element of the vector space. You can think of that as closure, right? This is closed. If I take one of these scalars and I use it to scale one of the vectors, that is still an element of the vector space. So we're not leaving the vector space by scaling the vector. That is analogous to this property over here. Using the operation to combine two elements does not take you out of the set. You're still inside the set. So we have closure. Closure is satisfied. And let's take this alpha to be 1. Let's take this to be the multiplicative identity. The multiplicative identity 1, scaling a vector, is just going to give the vector itself. So this is a lot like this property up here. If we multiply by the identity element, we're going to get back what we started with. So it does not change the vector. Scaling by a scalar that is equal to 1 is not going to change the length of the vector. And it's not going to change its direction either. So these are some fundamental properties. Now let me talk about the distributive properties. There are also some distributive properties that we need. If we take some scalar alpha and we are scaling a sum of vectors, let's call these vectors u and v, we can actually distribute this scalar to each of the vectors. That's going to give alpha times the vector u plus alpha times the vector v. And there's also another distributive property. If we have the sum of two scalars, alpha and beta, and we're acting on this one vector over here, so these guys are together scaling this one vector, we can use the distributive property, and we can have that this is equivalent to alpha times the scaled version. So this is a scaled version of v, so alpha times v, plus beta times v. So this is just like this property over here. We've got distributivity that links together addition and multiplication in a field. And these guys are also distributive properties. If we have the sum of two vectors and we're scaling that, that's the same as scaling the individual vectors and then taking the sum. And if we have the sum of two scalars and we're using that to scale a vector, we can distribute this vector inside, and that's going to give us a scaled version of the first vector, of this vector v, plus this other scaled version of v. So we're scaling with alpha and with beta. And alpha and beta are scalar quantities. They come from the scalar field. Another property that I want is associativity. So if I want to scale a vector that's already been scaled by another scalar, I can group these guys together. So I can group alpha and beta together, like this. So it's the grouping of the brackets. Where do the brackets go? That doesn't matter. It's equivalent. It's just like this property over here, the associative property for a group. So the ordering in which we group these guys together, that does not matter. That is associativity. So we have alpha times the scaled version of the vector is equal to alpha times beta all together scaling the vector. So this property is called associativity. It's an associative property. And these two properties together, they're both distributive properties. And you can think of this property over here as closure. And this property over here, this is the same as multiplying by 1. So multiplying by 1 leaves the vector unchanged. So for a vector space, the elements of the vector space, we reserve the special name of vectors. So vectors are elements of the vector space. And they can be scaled by members of the scalar field. And those are scalars. Now, I've used a notation where all of the vectors have little arrows. Both u and v have little arrows above them. So this notation is kind of analogous to what we use in physics, where a vector is a pointy arrow. So we have an arrow that points along a direction and it has a length. But that is a very limiting definition. It is very specific to only two-dimensional or three-dimensional spaces. So this can actually be an infinite dimensional space. We don't need to limit the number of dimensions. And in fact, there's an area of mathematics called linear algebra that deals with the study of vector spaces. And linear algebra is essential for quantum mechanics. And we'll be talking a lot about linear algebra and about vector spaces in subsequent videos in the quantum mechanics playlist. So this is a very essential concept of a vector space. So in general, these guys do not have to be pointy arrows in 2D or 3D space. They can be functions. They can be a whole array of different types of objects. And over here we have the operations of addition and multiplication. We don't have to limit ourselves to such operations. For group theory, you're not limited to just addition and multiplication. You could have symmetry groups or geometric groups where the reflections, translations, and rotations of physical objects are defined to be the operation. And the set of elements is not numbers, but rather physical objects of shapes. You have triangles, circles, squares, or three-dimensional shapes. All of that is actually covered by group theory. So these are immensely powerful abstract objects. And that is why abstract algebra is such an important field in mathematics, because of its physical applications. There are many physical systems that can be described with group theory. And fields and vector spaces can describe so many physical systems. This concept of a vector space is essential for quantum mechanics. And we'll be using the concept of a vector space to define a Hilbert space. And a Hilbert space is where the state vectors in quantum mechanics actually live. So the vectors live in the vector space, and we'll be talking about that in later videos. So just as a quick summary, we started with groups. We defined abelian groups or commutative groups, and then we used that definition to define fields. So a field is essentially two groups. So we have a set with two groups, two abelian groups with two separate operations. And those are addition and multiplication. And there's also the distributive property which links addition and multiplication together. And then we used an abelian group under addition of this vector space and a field of scalars to define a vector space. And we looked at all of these different properties, including the distributive properties and the associative property. And we remember that scaling a vector by 1 leaves it unchanged. That's analogous to this identity relationship over here. And we always have to remember closure is essential. If you combine two members of a set together with an operation, you want that to remain inside the set. So if you want more videos about these types of mathematics concepts, make sure to check out the quantum mechanics playlist. We're going to be using these mathematics concepts to describe physical systems. You can find those videos if you click over here.